Today's presentation will be, as I said, on the 10 satellites monitor crop and pasture quality across Australia. The project's aim was to conduct a feasibility analysis looking into existing and planned satellite missions, including the Aquawatch satellites and precursors, to test development of new high-frequency products for crop and pasture quality across the Australian landscape, and is a joint project between CSIRO and GRDC, funded by SmartSat CRC. Today's technical presentation on the results of the study will be presented by Dr. Ha Nguyen. And Ha joined CSIRO in early 2022 as a research scientist. Her background is in tropical ecology and remote sensing. She has used statistics and remote sensing to monitor landscape phenology in the academic sector, then crop growth with industry, and now she's with CSIRO. I'll hand over to you, Ha.
Thank you, Craig. Please let me know if you can't hear me very well, or if there's some adjustment to be made in terms of the volume. So again, my name is Ha, and I am a research scientist at CSIRO, working with Roger Laws out of the digital decision team. Before I begin to talk about what we can use hyperspectral imagery to monitor pasture and crop quality from space, I would like to emphasize that this is a team effort. We have pulled the expertise across the agency in terms of crop modeling, digital agronomy, remote sensing, and manufacture engineering. So we need to monitor crop and pasture qualities from space because at this current state, we know that farmers do not change practices just based on Earth observation data. We know that the current observed large-scale global changes in climate, population, and land use, land cover change has challenged farming to become more efficient, sustainable, and sustainable. Among all the most critical factors that affect crop yield, plant stress detection is has a real need to be detected on farm, in decision, and in season. And yet, despite the demonstration of utility, the scientific techniques that we know of, for example, field spectroscopy, multi-sensor data fusion, and crop modeling, are only adopted at very small scale and application. So in order to derive the synthesis, we have conducted simulation, mission simulation, literature review, and surveys into the user requirement and observational requirement to summarize the potential of space-borne spectroscopy or hyperspectral imaging in order to increase the efficiency of practical farming and address the gaps that has been holding up its adoption into precision agriculture as we see today. We would first talk about what we are going to measure with respect to pasture and crop qualities. We'll then talk about how exactly we are going to design such a hyperspectral sensor to measure pasture and crop quality. We would then talk about how the agtech industry can benefit from such measurements, and we'll close off by talk about our findings with regard to the hype with hyperspectral imaging. The first thing to keep in mind is that crop and pasture quality is indicated by plant biochemical and biophysical attributes. Crop and pasture quality is the result of cumulative stress throughout the growing season, and together they determine saleable yield. Insight into crop and pasture quality is useful for the grazing management in pasture and input management for crop. Crop and pasture quality included both state variables such as leaf nitrogen, leaf chlorophyll and growth stage, and rate variables such as evapotranspiration rate. Until now, multispectral imaging has been the holy grail to monitor plant growth and health. And so in the graph below, we are seeing the wavelength ranging from the visible at 400 nanometer all the way to the shortwave infrared region at 2400 nanometer. And on the y-axis, for all three plots, is the reflectance. Now, if we compare the top graph, which represent a typical vegetation spectrum in this region, the two most popular and widely used multispectral images, the Landsat 8 in the middle and the Sentinel-2, only sample the region ranging from the visible and very near infrared, which is from 400 to around 1,000 nanometer, leaving us two big gaps ranging from 1100 to 1300, and then from 1700 to 2100 nanometer. At a closer look, we also see that multispectral images does not closely follow what field spectroscopy observed in crops and pasture stress. In the graph here, a field compared to a field spectrometer can see, indicated in the black line. The German recently launched AngMap hyperspectral sensor can follow the behavior of crop and pasture much more closely in the red than compared to the Sentinel-2. Sentinel-2 in this case only agree with field spectrometer and spaceborne spectrometer in the visible and very near infrared. This spatial disagreement between spectrometer and multispectral imaging means that only by sampling the full spectrum, the visible, the very near infrared, and the SWIR, can we capture a full picture of the processes and behavior in plants. So if we only use multispectral, we would limit our own capability in monitoring crop and pasture quality. As the name indicated, hyperspectral means more and continuous spectral measurements. Compared to multispectral imaging here in the left, which only offer discrete and limited number of broadband spectral measurement, multispectral continuously sample the spectral region and hence offer greater ability to detect phenotypic parameter. And that's because higher number of narrow spectral bands means more sensitivity to reflected energies from different qualities. Different plant qualities can reflect this energy in their own narrow region, and hyperspectral can offer a closer look in this behavior both across the spectral region and in time. So in this picture, we are seeing what a healthy plant can, at the peak of its growth, can behave compared to what it can behave at the later stage, the Senescence period. This is a plot derived from the world's first operational and global hyperspectral sensor, the Hyperion, which unfortunately has stopped to operate. So we can see that hyperspectral can measure reflected energy both in terms of plant physiology. So in here, they can be structure, color, and stage. And the example of these plant biophysical variable range from leaf area index to plant height to crop chlorophyll and chlorophyll content, indicated here in the early region of the spectrum. Hyperion also revealed the potential of hyperspectral imaging in measuring plant biochemistry. So the SWIR bands, as indicated here, can infer absorption features from lignin, cellulose, protein, and nitrogen. However, we have to be careful because the caveat here is that there's also strong absorption features from water, which can mask such fine absorption from the plant biochemical quantities of interest, which is lignin, cellulose, protein, and nitrogen. Despite such caveat, hyperspectral can complement our existing capabilities in monitoring crop and pastures. And that's because they exploit the potential of the SWIR region, which corresponds to many biochemical attributes. These biochemical attributes will respond to climate change before the biophysical attributes start to show in terms of plant structure and color. And by using hyperspectral, we'll be able to derive early and critical insight into crop and pasture responses to stress independent of illumination condition. And our effort aligned with the development of essential agricultural variables, or EAV, by the Geo Global Agriculture Monitoring Initiative. In this table below, we can see that the essential agricultural variables, i.e. variables that are agricultural relevant, can be grouped into productivity, such as soil moisture, yield or crop condition assessment, to land use, such as field boundary, cropland mass, rangeland mass, and agronomic management, such as tillage, cover crop, and land management calendar. Among all these EAV, crop condition is the least defined. So in deriving these EAV, we hope to establish Earth observation-based building blocks that can provide actionable information into the stage, the change, and the forecast of agriculture, land use, and productivity. And in doing so, our effort in monitoring crop and pasture qualities from space address the requirement for greater quantification of agricultural activity and will drive requirement for Earth observation data and computing infrastructure post-2020. So in closing off this section, we start out with the question of what we can measure with respect to pasture and crop qualities. And what we can measure are the plant biophysical and plant biochemical attributes, with the requirement that they have to be measured from or infer from satellite data and need to be supported through field data for calibration and validation. As part of our report, we also conducted an industry survey, and this survey revealed that the trait of highest interest include yield, soil moisture, vegetation cover, disease and stress, protein content, and timing of different growth stages. We are next going to talk about how we can use hyperspectral imaging to measure pasture and crop qualities. First, we need to remember, go back to the textbook diagram of the fact that plants reflect more in the near IR, as indicated here, with the peak at 550 nanometer than in the visible at a peak of the near IR at the peak of 850 than in the visible with a peak at 550 and 1650 for the SWIR. So the different behavior of plant reflectance shown here means that if we sample the SWIR band together with the visible and near IR, we'll be able to have a complete picture of plant health and growth. And also, the inclusion of the SWIR band will enable novel and creative analytics to be developed for analyzing these hyperspectral data. We need also remember that denser sampling of the vegetation spectrum means a more detailed signal of plant physiology and biochemistry, because we can go from plant colors to cell structure or plant structure to the biophysical content of crops. But in order to do that, we first need to define the clear Earth observation requirement for such plant biophysical and biochemical attributes. The concept of a clear set of requirements is not new, but our contribution to this is that we are going to map out full and clear requirements for hyperspectral in measuring plant and pasture quality. First of all, we decide to focus on only the ag relevant parameter. So this variable must be biophysical or biochemically described in physical unit. They must be directly observable in the spectrum. They must be at a generalized species level, because otherwise species information is hardly known to the analyst at the time of analyzing data. And finally, the variable must be relevant to practical farming. So we formalize this clear Earth observation requirement for all the EAV. We map them out, not just in terms of the required parameter, but also in terms of the spatial, temporal, and spectral resolution, and also in terms of whether it is available in current and planned mission. What is available from hyperspectral sensor is reflectance. What we need to turn them into are the essential agricultural variables, and such is an analytical step. There are several methods to turn the reflectance into AAVs. The first family of methods assume a functional relationship between spectral observations and a variable of interest. The non-parametric regression methods will optimize the error between the extracted variable and the variable of interest. The physical-based algorithm apply physical laws to establish cause-effect relationships and infer variable using both radiative transfer model and canopy reflectance model. And finally, the hybrid method will combine machine learning with the algorithms, with the physically based algorithm methods. But what we need to remember is that these analytics are still at the nascent state of development. So the first case study of how such the reflectance can be turned into a variable of interest, we would be talking about grain protein content, or GPC. We know that accurate and timely assessment of within-field GPC would help informing variable rate application and selecting wheat lines with high nitrogen from the perspective of plant breeding. Yet so far, crop nitrogen status has been widely linked to and infer only from canopy chlorophyll content, and that's because the chemical structure of chlorophyll has a high presence of nitrogen. As referred to in a few slides back, we have mapped out the Earth observation requirement for grain protein content. And in order to monitor grain protein content from space, we need a spatial footprint of less than 15 meters, a weekly revisit, and the bands that are useful for grain protein content is the SWIR band. Previous research that only rely on multispectral imaging has only achieved very low discriminative power for grain protein content. So in this graph, on the y-axis what we are observing is that the R-square between what is inferred from different features of reflectance and nitrogen content is barely 0.2, which is hardly statistically significant. Not to mention the band selection is sensitive to the time during the growing season. In contrast, the use of the SWIR bands and full spectrum from field spectroscopy can achieve very high predictive power. In this example, a field spectrometer was used to collect reflectance across the spectrum and back out nitrogen grain protein content. And when compared with reference nitrogen content, the R-square is at least 0.77. So this provides great motivation to include the SWIR band and monitor grain protein content from space. So in here, in this this example has shown that the inclusion of the SWIR and full spectrum gave the model predictive power for grain protein content. The next case study is the orange rust in sugarcane. The study was actually carried out at CSIRO during the Hyperion active period. In the y-axis, we have wavelength ranging from the visible all the way to the SWIR spectrum. In the y-axis is difference in reflectance. And what we are seeing is that by using the SWIR band at 16 nanometer, together with the near IR band at 800 nanometer, and the green band at 550, we can maximize the difference between an infected plant and a healthy plant, and therefore a high discriminative power between between sugarcane with orange rust and healthy plants. In contrast, the use of only the Vernier IR or the red edge bands did not perform very well. So again, in this example, the inclusion of the SWIR and full spectrum shows potential for disease monitoring. In closing, we have mapped out that for crop and pasture applications, a hyperspectral sensor will need fine spatial resolution, high cadence or revisit time, narrow spectral bandwidth, and very high signal-to-noise ratio. And despite such potential as shown in grain protein content monitoring and disease monitoring, the SWIR region between 1100 and 2500 nanometer are highly underutilized. In reality, though, cost and operational constraints means that baseline field knowledge is required to select the most suitable sensor. And the most important thing is that to date, no single commercial or government or international instrument can meet all these specifications. And that's because signal-to-noise ratio of a hyperspectral instrument is tightly coupled to the spatial and spectral resolutions, and therefore the cost and capability of a hyperspectral sensor. Our team has, in order to understand such trade-off in between these specifications, what our team did was to conduct a simulation comparing the case of an ANGMAP satellite at 30 meter spatial and 10 nanometer spectral resolution in the blue, an improved spatial resolution in the green, and an improved spectral resolution in the orange. And what we found is that going in higher spectral and spatial resolution only lower the SNR requirement and therefore fail the agriculture requirements for hyperspectral. Anything with a lower SNR, lower than 100, would seriously jeopardize the ability to retrieve plant and crop and pasture quality from hyperspectral. So hyperspectral is not the end-all be-all solution to precision agriculture. Let's not forget that multispectral resolution can provide higher spatial resolution because in hyperspectral, the latter is sacrificed in order to maintain a high signal-to-noise ratio. So the best of both worlds approach here is to combine the strength in multispectral, which is spatial and temporal resolutions, with the high spectral resolution in hyperspectral as a fusion product. Furthermore, what we can consider is to operate all these missions as a virtual system in a coordinated manner, such as that all the missions can overlap in coverage. And in that way, they can together meet the Earth observation requirements we have set out for the crop and pasture parameters. So given these requirements, how can the agtech industry can benefit? In this diagram here, we are observing a global influx of hyperspectral satellite going all the way into the end of this decade. The red colors indicate government launch and plant mission, whereas those in the blue indicate efforts from the private sector. In this future of hyperspectral missions, the race to launch has prevented a global and operational hyperspectral system. We have not seen to date a detailed, high quality, and reliable acquisition scheme for hyperspectral data. Yet the global hyperspectral imaging market is set to double in value by the end of this decade. This market is dominated by only the very near infrared hyperspectral imaging segment, and it is challenged by high cost of equipment and high volume of data per sensor and from all missions. And many of these constellations will trade the SWIR band for increased temporal and spatial resolutions. None is intended to have long mission life. So in order to understand the view of the industry, we interviewed 5 5 companies that offer insight as a service or software as a service in the agriculture, climate and sustainability sector across the US, EU, and Australia. What we found is that large amount of satellite data do not automatically lead to more efficient farming. They emphasize instead on time-sensitive, which is during the growing season, low latency, and analytic-ready data that are ground truth and scientifically proven. More bands and higher resolutions to the industry, unless they can assist in solving the problem fast, at the time of need, at field scale, and at the right cost, they are of no use to industry. And finally, despite the number of launch and planned missions, most of these missions are very similar in specification, and they don't have a specific use case design or the analytics developed to handle such volume of data. So in order to make the Earth observations benefit from hyperspectral obvious, we need to invest in analytic or application-ready data, ARD for short. So these, and that's because these, the user need data that are tailored to the specific need of farm management. So ARD here are satellite data that have been processed to allow immediate analysis with a minimum additional effort. And these ARD require detailed metadata, consistent atmospheric correction, excellent cloud, snow, and shadow masking, and historical archive in order to derive either baseline or anomalies analysis. So, and further, these ARD need further refinement to directly address the requirement of specific farming decision. Effectively, we are here in the process to turn data from sensor to a state where decision can be made and actualized on the field. And in order to take data to the state where decision can be supported, made, and actualized, we need calibration, validation, spectral libraries, analytics, and finally models. Models that can ingest this data into decision support. So in closing, what have we found with respect to the hype of hyperspectral imaging? We observed that there's a trade-off in realizing the potential of hyperspectral for the ag industry with a cost at which they can operate with. So it is very important to be able to anticipate, to simulate, and to understand such trade-off so that we can design a relevant and impactful mission. So the next frontier is a fusion product, which is instead of a mission-specific product that can cater to practical farming, which are outlined in terms of the list of essential agricultural variables, as well as their Earth observation needs. We also observe a research gaps in retrieval algorithm in plant biochemical and biophysical variable, which can be resolved with machine learning and ground calibration and validation data set. We are here today, well, we set out this report and pilot study to discuss the design of a mission. But in closing here, we actually recommend looking beyond a single mission into a future where all hyperspectral mission can be ingested into a system that enable decision making and the actual actuation of such decision. And in that future, we don't just need data, we also need data for calibration, validation, spectral library, analytics or algorithms, and models. The strategic position for Australia's sovereign interest in agriculture and space rests on the augmenting of such EO with calibration and validation. We need ground segment, we need on-farm, in-situ, localized technologies to zone in the local area of interest We need calibration validation. We also need product development and scientific application. And at CSIRO, we already are developing autonomous scouting platforms to scout on the ground. We already have operating field stations with trials and experiments running for different plant cultivars and species. We also have collected measurements and spectral libraries from handheld instruments. And also we develop tools for nitrogen recommendation, for yield prediction, and for detection of field boundary. In the past, HiMap is another instrument that was manufactured in Australia and was actually recommended by NASA researchers because they offer a very high signal-to-noise ratio, as well as image quality that set the standard for industry. However, only sporadic data campaigns were collected with HiMap. Currently, with the AngMap, we are evaluating its potential over the Baroa Research Station. With a flyover happened actually last week. We also have surveyed the field at bars with a drone and a handheld spectrometer, and we have scheduled more surveys to be taken place. What we observed is that hyperspectral from the AngMap sensor cannot see through clouds. At the moment, the product level 0 from AngMap was already available. There were 20 overpasses for Southeastern Australia, and most is with cloud cover. This is an example of what AngMap saw over an area in New South Wales in September this year. And as you can, and half of this image is covered with cloud. Again, the latency or the time lapse between when an area was scanned and when the imagery was available is 5 to 8 days. So what the message here is that hyperspectral as a single technology will not solve all the problems we're facing in precision agriculture, and it will not solve what multispectral cannot solve. So in doing what we propose here is to extend the Australian Geoscience Data Cube concept to include multiple wavelengths, multiple scales, and multi-layer analytics. So at the default layer, we'll have the already operating multispectral and global missions such as Landsat and Sentinel. But the next one, we propose to have hyperspectral imagery tasking locally by demand. And finally, we propose to have hyperspectral as a persisting local tasking for monitoring at the station, with Baroa being the pilot study, the pilot case. In doing so, we are demonstrating the business model for farming as a service by CSIRO. We can partner with satellite providers, source calibration and validation data, design and uphold protocol, and also develop product and algorithm. Our vision is that the output from such farming as a service business model will produce these essential agricultural variables as crop biometric layer. So these layer can be different. Each layer can represent a different crop and pasture quality. They will be temporally updated with new data and spatially explicit, and together they will hold the key to building prediction models for crop yield. So in closing, the problem we are facing is that farmers do not change practices based on Earth observation data, and specifically, they do not change practice just because there are now more bands from a hyperspectral sensor. We know that hyperspectral can greatly augment our existing capability in monitoring vegetation growth and health. We established that a fusion product that treats all hyperspectral sensor as one virtual constellation, and hence common calibration and correction procedure is required. And we also established that current research gap in the retrieval of essential agricultural variables can be resolved with machine learning, with ground calibration and validation, and with careful design of product. And in this global influx of hyperspectral mission and data, the strategic position for Australia is to develop world best practice use case for hyperspectral mission. And at CSIRO, we believe we have the unique and complete competence to provide such end-to-end solution to deliver such vision. So this pilot study was supported and jointly funded by CSIRO, SmartSat, CRC, and the GRDC. Yeah, this is the end of my presentation, and I would be very happy to take any questions. Thank you.
Thank you very much, Ha. That was a very interesting presentation. I was particularly interested to see your emphasis on the SWIR data, which has been largely ignored by the agricultural sector up till now. Mining has been much more prevalent in that area. So I'd like to invite anyone to ask questions now. You can put them into the chat if you'd prefer me to read them out.
I have a question. Ha, that was great. Thank you so very much. That was excellent talk. You know, when I saw your poster at the SmartSat conference, I was really keen to see this and see in action the details of this. Do you mind actually if we go back to slide 30? I'd like to poke or understand a few things in there.
Yep. Slide 30, for sure. Yeah.
Yeah, what I wanted to understand this one just a little bit more. Is this assuming that the sensor is equivalent in all cases, and you're effectively just changing the optics, the telescope on the front end to give you this different signal to noise? Or I guess I didn't quite understand what you changed or varied in this scenario to give you this varying SNR.
Yeah, so actually this plot and this simulation was actually produced by my colleague, Dr. Joshua Pease in Adelaide. I think Joshua is among the audience here, but before I, that's my belief that, Carl, you're correct. Carl, you're correct. I believe that all else being held equal, what we are changing is just what is indicated here in the plot, and it's all look at the same typical agriculture scene. In doing so, we can understand the trade-off. And so I believe that's what's happening here. But Josh, do you want to add anything to this, the explanation here? Let's see if Josh is still among the audience. Did I answer your question?
That's okay. We can move on to
iterate over
follow on.
Yeah,
you know, and to Craig's point too, it is good to see the SWIR as well. And can I ask a perhaps uneducated question? Would you have a hyperspectral that covers this whole range, including the SWIR? Would it be a single imager, a single single imager to actually cover that whole range? Or is in practicality, would you have multiple perhaps sensors that covered this range?
I believe that, you know, like it is all else being held equal. Yes, it is physically possible to design one single sensor to cover the entire range. So then the next question, though, is at what spatial resolution would you like to have, and for what use case? As we demonstrated, it is physically possible. It's just that what SNR will we have, and whether that SNR warrants the retrieval of an application that we are interested in. That is what we are looking into. Other than that, you know, like having separate is okay. There are several companies that, as I mentioned, only decided to focus on the first segment of the spectrum. There can be other companies that can see the use case of the SWIR bands as we have mapped out. But in order to do that, you know, we need to really design the use case and really make the application of the SWIR bands more outstanding. Otherwise, the trend that we have seen is that satellites that cover the full range will suffer in terms of revisit time and spatial resolution. I mean, the EngMap certainly cover the full range, but the revisit time is like 27 days, if I'm not mistaken, and the spatial resolution is at 30 meters. That's my opinion. Yeah.
Thank you. And my final question before we hand over here to Chris, who is patiently waiting. You mentioned this failing agricultural's high requirements and getting it above 400. There's only a limited range even here that's above 400 for this. I know this is just an analysis to do a comparison, but does this imply if we need to get both the lower wavelength and that higher SWIR wavelength up above 400, does that mean we're talking about ultra capable, very expensive images and sensors? And how far off are we from actually flying something that would actually meet above 400 SNR, still give you the spectral resolution and the spatial that you really would need here for the agricultural sector? Do you have a feel for that?
So I'm trying to understand your question. That is like, given that this is the standard or the optimal requirement for SNR, how far off are we currently operating? Like, how far off are the current missions from making such requirements feasible? This is a hard question. I believe that, so for example, this 400 figure here is the requirement that ENMAP is trying to meet. Yet in trying to meet that, they are still at 30 meter spatial resolution and 20 meters revisit time. So even though SNR is met, we are only at the stage of having the data ready for analysis, right? Whether it can be applicable to agriculture application, there's still several steps to go forward. So that's my official that's my response to your question. So we need to invest. Yeah, we need to invest in more than just sensor. Basically, that's the short answer. Yeah.
Yeah, and I think what perhaps the answer that, if I try to reword your answer there, it's an MMAP class imager to get close to this 400:1 SNR.
Yeah.
Is what we're talking about. If we want an agricultural application, that's the kind of class of imager, cost, size, specs that we're looking at. So that's great to hear. Well, thanks, Ha. This is great, and thanks to the team as well. I know they're all online, so thank you. I'll hand over to Chris.
Ha, I really enjoyed your presentation. As an astronomer by background, divide your signal to noise ratio by 100, and that's what I'm used to thinking about. So can you comment on the potential to change the requirement? So why is 400:1 so important? And has that really come from a world of multispectral imaging that's perhaps not as relevant when you have so much information available to you through hyperspectral?
So the first thing is that I believe that the 400 figure was, so basically it came from, this is a figure that we drawn from several specifications, not just for the ANMAP, but also for the Prisma, which is the Italian mission for hyperspectral. I don't think that this, the second one is that, to compare hyperspectral SNR and a multispectral SNR is very hard because, as I said, they have different strengths. But yeah, so can you also, I think that that's a part of your question that I could understand, but can you, follow up with what more you want to ask? Yeah.
So why don't you advocate, or the appropriate bodies advocate, that the requirement should be 300:1 or 200:1, because there's more than enough information in the hyperspectral bands in order to uniquely measure what it is that you're trying to measure. So 400 seems so arbitrary to me, and so you're trying to find a technology solution that might get to 400 but what if you could get a sufficiently good answer even by only getting to 200 or 300 to 1?
I think my multispectral, actually, like the SNR for multispectral is actually not that high. So I think, like, to really achieve an SNR here, again, yes, it is arbitrary, but also, like how multispectral and SNR is only one aspect, only one technology. We certainly can combine this and not getting too caught up in the SNR alone, and combine it with other technologies to realize the use case and the extraction of the features of our interest. So SNR alone, yes, it's just one aspect, and so we shouldn't be too caught up in that.
Great, thank you.
Thank you.
Okay, I've got a question in the chat box from Phil Tickle. Given your recommendations to fuse MSI and HSI, how would you intend to reconcile the likely differences in capture time?
That is a very interesting question. So actually, in this case, let's take the so this is about how we can provide a fusion product. So let's take as Sentinel as our example for multispectral, and let's take the EN map for the hyperspectral imaging. Sorry, as an example for our hyperspectral sensor. I believe that, so the first step is that we can only, like, align the best we can between any paired of imaging between Sentinel and what else? Between Sentinel and EN map. But I believe that reconciling the difference in sensor time is only one aspect. What do we get from reconciling of that time? Like, we also need to know because I believe there are other aspects that we need to reconcile after just the time of acquisition. And finally, we need the ground data to make sense of what we really get from such fusion in terms of time difference in acquisition. Phil, did I answer your question quite well? Feel free to follow up in email or in the chat.
Thank you for that, Ha. Are there any other questions from anyone? Well, I just had a comment on the signal to noise ratio discussion.
Sure. Yeah.
From my experience with an airborne sensor, we were looking for very high signal to noise ratio because many of the features that we were actually trying to tease out, and this was related more to the geological side of things, up in the SWIR bands, you are getting less signal up at those higher bands. And some of the features you're looking for are very, very small. And once you start getting down to that 200 to 1 or 300 to 1 sort of range, you're actually losing those very small responses in the bands to the noise, and you can't actually discern that. So whereas a multispectral's got a very wide band, it's less sensitive to those noise characteristics. Once you get very narrow bands, it becomes very important to have a very high signal to noise ratio to get those features.
Yeah, that's great. Thank you.
All right, if there's no further questions, I'd like to thank you, Ha, for a wonderful presentation and some really great work across this project. And also thank you to everybody for attending this session.
Thank you.